Welcome back everyone. In this lecture I will actually continue the classification of three dimensional Lie algebras. Okay, as we have seen, so we have seen one case. So let us recall what we have done so far. So we want to classify three dimensional non-abelian Lie algebras. We already classified one case, which is the Heisenberg Lie algebra. So, what is that case? It is characterized by the following properties. So, the dimension of G is 3 and the dimension of the derived algebra is 1 and the derived algebra is contained in the center. So, if the Lie algebra G satisfies these conditions, so then we saw that this will be isomorphic to the three dimensional Heisenberg Lie algebra. Okay. So, today we will actually continue the classification. We will deal with other cases. So, the case 2 which will be again dimension 3 and the derived algebra will have dimension 1, but we assume that the derived algebra is not contained in the center. Okay. So, before actually getting into the classification, let us see one example. So, which is I already told you how this Lie algebra should look like. So, if you take G to be G2 non-abelian, direct sum G1 abelian. So, what is G2 non-abelian? So, let us recall that. So, this is nothing but two dimensional algebra which is let us say spanned by x and y, then the bracket x y should be x. Okay, that is a this two dimensional non-abelian algebra defined. What is this one dimensional abelian algebra? It is generated by let us say some w such that just the bracket of w is 0. Okay, so, this is how these two algebras are characterized. So, now if you take direct sum of these two algebras, so then what we get, it is easy to see that the derived algebra is nothing but the derived algebra of non two dimensional non-abelian. So, which is actually just spanned by this x. Okay. So, that means this is one dimensional. So, similarly, what will be the center? The center of G is nothing but center of G2 non-abelian plus the center of G1 abelian, but there is no center in the G2 non-abelian. So, you get this equal to center of this G1 abelian, which is just G1 abelian. So, again this is also one dimensional, but you can see the bracket Gg is not contained in the center G. Indeed, what we have, the bracket Gg intersection with the center is 0. Okay. So, this is a very special example. So, now we will see whether our conditions for the case 2, okay, that characterize this Lie algebra. Okay. Indeed, we will prove. So, if you have a three dimensional Lie algebra satisfying the conditions in 2, then G must be isomorphic to direct sum of this G2 non-abelian and G1 abelian. Okay. So, let me state it as theorem. If G is a three dimensional Lie algebra such that, again over complex numbers. So, that is very important. then the dimension of the bracket GG is 1 and the bracket GG is not contained in center of G. So, then one can prove that G will be isomorphic to this direct sum of 2 dimensional non-abelian and 1 dimensional abelian. Okay. So, this is our theorem. So, let us prove how one can prove this. Let us see how one can prove this theorem. So, here is the proof. So, again we establish a basis, that basis will have exactly the structure constants of this direct sum. Okay. So, that is the idea, because we are dealing with very small dimensional Lie algebra. So, this is actually possible. So, let us see what we can do. You start with some x inside G such that this x is actually not in the center, okay, because the center is not entire G. So, G is non-abelian. So, this is possible. Since this x is not in center, so we can choose y inside G such that the bracket x y is non-zero. Okay. So, then it is immediate that x and y are linearly independent. So, this exercise we already done. So, now you can see that since this bracket x y is being non-zero and the dimension of this derived algebra is 1. So, that would imply the derived algebra is just a span of this x y. Okay. So, you have already, so maybe what we can do, we can actually choose this x from the derived algebra itself, okay, because the center of G does not contain this derived algebra. So, one can make this choice that this x is actually coming from the derived algebra. Okay. So, since that does not contain, center of G does not contain the derived algebra. So, we choose x in the derived algebra such that x is not in the center. So, now using that x, we also take this y such that the bracket x y is non-zero. So, I am going to use those x y. Okay. So, now because x is coming from the derived algebra and this bracket x y is also in the derived algebra. So, that tells us that this bracket x y should be multiple of x. Okay. So, what does it mean? It means there exists alpha in C which is actually non-zero such that the bracket x y will be equal to alpha x. Now, we can rescale this y, okay, rescale the y as 1 by alpha y. Okay. So, then we get bracket x y to be x. So, now note that the span of these two elements x y. So, that will be isomorphic to G2 non-abelian. So, by the choice. Okay, we have established one 2-dimensional Lie algebra inside this G which is isomorphic to G2 non-abelian. So, now what we do? We extend this x y to a basis. Okay. So, extend this x y to a basis of G. So, call it x y w. Okay. So, then what happens, you can see that, so this is going to span G. So, in particularly since x is actually spanning the derived algebra G G, if I compute x w, it will be some multiple of x, and if I compute y w, again it will be some multiple of x. Okay. So, for some fixed a b inside C. Okay, this is what we get. So, now what we are going to claim? We are going to claim that the center must be non-zero. Okay. We do not know anything about the center, all we have actually assumed that the derived algebra is not contained in center. So, center could be 0 also, we do not know, but we are going to say now the center must be non-zero, we will be able to pick one very nice element from the center. So, for that what we will see, so we will just characterize the elements of the center and then see we can make a choice for that kind of element. Okay. So, if something is in the center, let us say Z. So, that Z must look like some lambda x plus mu y plus gamma w, because x y w that will span this G. So, this is in the center, you can see that if and only if this Z must commute with x and y and w. Okay. So, this will be the characterization of Z. Now, if you do the computation, you can see if you compute x Z, then you see that this is exactly equal to mu plus gamma a x. Okay. Similarly, if you compute y Z, then you get minus lambda plus gamma b x. So, this is what this computation says. So, now you can make a specific choice for lambda, mu and gamma. For example, you can take gamma to be 1 and mu to be minus a and lambda to be b, okay, because a, b are fixed, I can make this choice. So, then we immediately get the bracket of x z is 0, because gamma is 1, mu is minus a, and similarly the bracket of y z is 0. Okay. So, now you can see that this z of the form b x minus a y plus w, okay. So, which is actually commutes with all other elements. Okay. Why? Because Z x y also will form a basis for G. Okay. Z is already commuting with x and y, and Z will commute with itself. So, that will imply Z commutes with everything. Okay. So, since the coefficient of omega in Z, that is non-zero, you can see that Z x y form a basis again. So, this proves that G has another basis C x, C y, C z, such that Z is in the center and this x y is going to give us x. Okay. So, that means if you put them together, you can see that this will form a 2-dimensional non-abelian algebra and this will form a 1-dimensional algebra. So, G will be isomorphic to G2 non-abelian direct sum G1 abelian. Okay. So, this actually is a kind of characterizes this particular Lie algebra using those conditions in case 2. So, now I will actually skip case 3, which I leave it to you to work it out. Okay. What is case 3? Case 3 is the dimension of the regular the derived algebra is being 2, and one can prove there are infinitely many non-isomorphic Lie algebras of this type. Okay. So there are infinitely many. Lie algebras of this type. Okay. So, we will actually focus on what is in the case 4. Okay. What is case 4? It is just the dimension of G is 3 and G equal to bracket GG. So, because dimension of the derived algebra being 3 is equivalent to saying that G is equal to the bracket GG. Now, what we claim? We claim that in this case G must be isomorphic to SL to C. Okay. So, this is actually a very important case. So, in the 3-dimensional Lie algebra, the derived algebra being equal to G characterize SL to C. So, this is actually bit of non-trivial result. Okay. So, let us see how one can actually approach this. So, for this actually one needs to know about Jordan canonical form, but anyway it is not that important, one can actually try to establish Jordan canonical form as well. But anyway let me recall what is the statement about Jordan canonical form that we need, okay, and then I will proceed. So, which I will not prove again. Okay. So, if you have a linear map from 3-dimensional space to itself, let us say V is vector space over C and then the dimension of V is 3. So, let us say T is a nilpotent operator and the rank of T is 2. So, then what we can prove, there exists a basis of V such that, so there exists a basis V 1, V 2, V 3 of V such that the matrix of this T with respect to this basis will look like this. So, this is the Jordan canonical form of this operator T. Okay. So, this I will leave it as exercise. So, this is a very simple exercise because we are working with very smaller dimensional vector space. So, for this nilpotent operator that is having rank 2, okay, we will have this particular Jordan form. Okay. So, this will be used in this classification. So, okay, let us see how one classifies this 3-dimensional Lie algebras whose derived algebra is itself. What is the step 1? So, we start with non-zero vector, okay, inside G and then look at this add x. So, which is a map from G to G. Okay. So, since the derived algebra is actually 3-dimensional, okay, so this add x must to have rank 2. So, add x has rank 2. Why? For example, you can take a basis that extends this small x. Okay. So, let us take x, y, z basis of G. So, then it is not hard to see this derived algebra. So, that will be spanned by x y, x z and then y z. Okay. Since there are only 3 elements that is spanning this derived algebra and the dimension of this derived algebra is 3. So, all of them must be linearly independent. In particularly x y and x z, they are linearly independent. Okay. But both of them lie inside image of add x. Okay. and you can see that the kernel of add x contains x, okay, the kernel of add x that contains x. So, that implies the nullity of add x is 1 and the rank of add x is 2, and this is true for all non-zero elements inside G. Okay. So, now let us use this information to get a element inside G that has actually non-zero eigenvalue. Okay. So, that will be our step 2. So, what is the claim? Claim is there exists non-zero element inside G such that add H has non-zero eigenvalue. Okay. So, with some non-zero eigenvector. So, if you think about it, okay, so what is the meaning of add H having non-zero eigenvalue? So, if all the eigenvalues are 0, then it will say that add H must be nilpotent. Okay. So, it will be a theorem which is will be actually proved later called Engel's theorem. Okay. If we actually use Engel's theorem directly, then what it says? It says G must be actually nilpotent Lie algebra. Okay. So, I have not defined all those things, but it is just a remark that I will make as a side note. Okay. Suppose add x is nilpotent for all x in G. So, then what one can prove that G must be nilpotent. So, this is actually theorem of Engels. Okay. So, in particular what we get that the bracket of G must be proper. Okay. That is true for any solvable Lie algebra. So, that must be true for this nilpotent Lie algebra. So, that is why once we start with G being equal to the derived algebra. So, we always we must get some H in G such that add H has non-zero eigenvalue, because add H should not be nilpotent. Okay. But anyway, we will actually prove this result using Jordan canonical form. So, that is not very hard. Okay. So, now you start with x in G. So, then if add x is add x has non-zero eigenvalue, so then we are done. Otherwise, what will happen? Add x becomes nilpotent, okay, because it does not have any non-zero eigenvalue, all the eigenvalues are 0. So, it is nilpotent. So, we already seen that from step 1, this also has rank 2, okay, add x has rank 2. So, that means, so if you look at this Jordan form of this add x, okay, as we said before, it will look like this way 0 1 0 0 0 1 0 0 0. Okay. So, that means you are able to find a basis. The basis you call it x y naught z naught, because x is actually in the kernel, okay, that x will corresponds to the last column. So, you get this basis such that the bracket x y naught will be equal to z naught. Let us say first column corresponds to y naught, the second column corresponds to z naught, and the third column corresponds to x. Maybe I will reorder this. Okay. So, this is y naught z naught x. So, that you get bracket x y naught is z naught and the bracket x z naught is bracket x z naught is x. Okay. So, now you can see, even though x does not have any non-zero eigenvalue, this equation immediately tells add z naught has eigenvalue minus 1, because z naught x is nothing but minus x. So, x corresponds to eigenvector of add z naught with the eigenvalue minus 1. Okay. So, that proves we always have a eigenvalue we have a vector h in G such that add h has a non-zero eigenvalue. Okay. Now, what is step 3? So, you pick such actually h. Okay. So, now by scaling this h we can also make that h to have any eigenvalue. For example, you can take h to be twice z naught, then it is clear that add h has eigenvalue 2, okay, sorry minus 2. Why? Because h x will be 2 z naught x, which will be twice minus x, which is minus 2 x. So, this tells us that we can rescale this z naught and then get any eigenvalue that we want. So, we better keep this minus 2, because that is the eigenvalue that we had for the standard basis for SL2. Okay, now, this h is actually coming from where? It is coming from G, which is nothing but the derived algebra. So, because this h is coming from the derived algebra, so this h can be written as sum of some x I y I, where I ranging from 1 to k. Okay. So, that means if you look at add h, then the add h will become summation add of this bracket x I y I ranging from 1 to k. So, now if you rewrite this, this means this add h can be written as bracket of add x I add y I and then their sum. That means the trace of add h must be always 0, okay, if it comes from the derived algebra. Okay. So, since h is coming from the derived algebra. So, that means if minus 2 is actually a eigenvalue, then plus 2 also must be eigenvalue. Since h is 0, so that says 0 is already an eigenvalue. Okay. We proved that minus 2 is an eigenvalue. Since the trace of this add h is 0, so that says 2, 0, minus 2, all of them must be eigenvalues of add h. Okay. So, because we have only 3 dimensional space, so this will actually gives 3 distinct eigenvectors. So, that will be linearly independent and that will form a basis for G. So, we will take that basis and work with that. So, you call x is corresponding to the eigenvector corresponding to the eigenvalue 2 and h is already eigenvector corresponding to 0. So, this y you call it corresponding to the minus 2, maybe I already called it x, maybe we will stick with that. So, x will corresponds to minus 2, okay. Maybe rewrite this. So, call this y corresponds to 2 and then x corresponds to minus 2. So, there is no harm in this. So, now if you actually do the calculation, what you get? You get h x equal to minus 2 x, h y equal to plus 2 y and h s is 0. Okay, this is what we are getting. But let us look at this bracket y x. You take h and then calculate this, how this add h act on this y x. You can see using the Jacobi identity, because this corresponds to the eigenvalue minus 2, this corresponds to the eigenvalue 2. When you take the bracket, that should corresponds to eigenvalue 0. So, that can be verified using the Jacobi identity. So, the Jacobi identity says, So, this will be bracket x y x plus the bracket y h x. So, that means this h y will be 2 y x plus this h x will be minus 2 x. So, that means you get 2 y x minus 2 y x. So, that will get cancelled, you get 0. So, this proves that the bracket y x is inside the kernel of add h. So, which is already we know one dimensional, which is C h. So, that means this bracket y x should be some alpha times h, and this alpha also must be non-zero because the bracket y x is non-zero. Okay. Why this bracket y x is non-zero? If y x is 0, that will imply x is in the kernel of add y, but already y is in the kernel of add y. But we have seen from the step 1 kernel of add y that has only dimension 1, okay, that will be a contradiction. Okay, there cannot be 2 elements here. So, that is why this bracket y x must be non-zero. Okay. So, that implies alpha non-zero. Now, by rescaling your things and then switching back, okay, maybe you switch to call it x dash to be y, and then you switch this y to, okay, y dash to be alpha inverse y, and then sorry, what I have written, alpha inverse x, and then h to be h dash to be h. Then you can see that h dash x dash, which is h y, is nothing but 2 y, which is 2 x dash. Okay. So, similarly, this is 2 x dash and h dash y dash will be just minus 2 y dash, and similarly x dash y dash will be h dash, okay, because this will be just h. So, this is already looks like a basis of SL to C with the same similar the structure constants. So, that means the Lie algebra that we have actually talking about, that will be isomorphic to SL to C. Okay. So, this completes the proof. So, here kind of we use this Jordan canonical form, but later actually I will recall and then try to actually give some ideas about this Jordan canonical form, okay, which will be again later used very much in the structure theory of semi-simple Lie algebras. But anyway, I advise you to actually revise this Jordan canonical form and its proof if you have actually haven't seen. So, it is better to go through the proof before actually getting into the structure theory of semi-simple Lie algebras, because this Jordan canonical form, the additive version of that will be very much used. Okay, I will stop here and then we will continue in the next lecture with the definition of solvable nilpotent Lie algebras and their basic properties. Thank you.